Hello guys, welcome to our seventh episode of the DevStandup, and today we have a guest speaker, Sruti. She's a lead data scientist with end-to-end experience in data from engineering and business intelligence to AI. Currently, she's focused on solutions using the Snowflake Data Cloud and N8N. She also loves the coffee, as she mentioned here. And about her topic, it's gonna be like she's gonna talk about time series analysis, which is focused on the core understanding of forecasting using data and conducting a small case study on demand forecasting in retail supply chain. So without further ado, I'm gonna give the floor to Srutimala, and she can basically start the presentation.
All right, so as mentioned, we'll be talking about time series forecasting. It will be accompanied by a mini case study in retail supply chain. So, what is forecasting? Forecasting is, simply put, it is the science of predicting future events based on the patterns of the past. And when we say past, we mean historical data. In this session, we'll be focusing on forecasting, and especially forecasting versus prediction, because it is a very common question that people ask. When do we use forecasting? When do we use prediction? So we'll be clarifying that. Second, we'll move into the basic high-level steps involved in a forecasting analysis. And thirdly, we will walk through a very basic example of doing demand forecasting using retail supply chain data, of course, from Kaggle. So let's move on to the next part. So forecasting versus prediction. So once we know this difference, we will know exactly what forecasting is on its own. So forecasting is nothing but it is a type of prediction, but there is a temporal component attached to it. So when we say we forecast, we use the past data as well as the present data to estimate the future events. So very much time related concept. But when it comes to prediction, it is more of predicting a certain outcome, and it does not involve any temporal element to it. So we look at the relationship between different variables or fields in our data, and we predict a particular outcome. So to clarify this, there is an example on the right if you see. So when we forecast, it is usually from the perspective of the larger company or the business. So which aggregates over time. So example, if I am asked what is the projected sales for a product in my company in the next quarter, then we will solve this problem or will answer this question using a forecasting solution. While in the prediction part, it is more of an individual outcome, right? So if I ask what will be the probability of a specific customer purchasing my product, it will go into a prediction solution. So we'll build a predictive model, and that will be our solution instead of a forecasting solution. So that is basically the difference between forecasting and prediction. I hope it is clear. So moving on to the next part. So forecasting is part of a machine learning concept as well, especially the time series analysis. And any machine learning solution goes through certain types of steps. In here also we'll follow similar steps, but actually the granularity of those steps are different, as we will see in the code. So starting with the first step, we get the data, we get the relevant data based on our business understanding, based on the availability of data in our system. And we gather the data and we prep the data and we explore the data. As in, we try to understand and visualize the trends, the seasonality, and other components or the distribution of data as a whole. So that is the first step, because understanding the data will help us in our next step, which is the model selection and the training. So in the second part, based on the analysis we did in the first, we will understand what complexity of model or algorithm will actually suffice for our problem statement. Here we can choose any forecasting method. It could be ARIMA or exponential smoothing. It could be a moving average. There's a lot of other options. Or even XGBoost, which is a very common model. So this is the second step, and moving to a third step. Once we have our model trained, we will evaluate the model on some known ground truth. So in machine learning, when we say ground truth, we mean the actual data that we have in store. As in, if we have a data from, let's say, 2022 till today, then a big chunk of that data will become our training set, but we'll hold out a small set of data for our testing, where we have the actual data or the actual event happening, so that we can test our model on it and we'll evaluate whether this model will suffice for our business. If not, we will improve the model, which is part of our third step as well. So in our case, we will take the forecasting model, we will do future projections, and we will evaluate and improve the model incrementally. So these are basically the high level steps in forecasting. So as promised, we will move into the case study very soon. Let's define the problem statement first. So we are taking a retail company because we have the data, retail related data from Kaggle. So here in retail, let's say, managing inventory is important, right? We need to fulfill all the requests, but we also have to ensure that our inventory is not overflowing with products, but is also not, we do not have stale products in our inventory. So that balance is very important. And in order to do that in our business, we have to, the solution basically lies in doing demand forecasting of the product. So that, let's say I'm in September right now. If I want to understand what is the amount of product I need to store, I need to understand the demand in the next couple of weeks or months for that particular product. So demand forecasting is what we'll be doing in order to solve this problem. All right, I'm moving on from this to our code. So hopefully you can see the screen. All right, so this is in Google Colab, very handy when it comes to creating solutions on the fly. All right, so using Python language, of course, I have imported some basic libraries as usual. The data is called retail store inventory data. So these are the fields that we have in the data. So basic fields that you can imagine. So if I have a single store or multiple stores, for each store, I will have multiple products, how many units are sold, how many units were ordered for the inventory. All of these details will be part of my data, and maybe some additional data as well. Let's say the weather, maybe some marketing campaign, all of these things could be a part of this, the original base data as I call it. As you can see here, holiday can also be a part of this. So let's say we have chosen the data and the fields as we see necessary. And moving on, the first step will always be to process our data. In our case, we have multiple rows of the same product. That is the shape of our data. So what we'll do is we'll aggregate the data on that particular level. So this is a case by case basis. This is not exactly a template we follow. So this is based completely on the data structure that you have. So moving on, after processing the data so that we can actually go ahead with the exploration part. So coming to exploration, it could start from a basic exploration as in understanding what are the fields that we have, what are the minimum maximum values that we see. It could be the mean, median, mode, all of this distribution or statistical matrix that we can see in the data. But apart from that, we can also look at the visualization, which is more handy when it comes to forecasting. We can look at the distribution of units sold. So let's say this is pretty normal distribution. If you know what normal distribution means, it is bell-shaped curve. Let's say this was a little more skewed than we see normally. So based on this understanding, we can transform our data into more normal format if it is required. So that is why this exploration is crucial, and it is the first step of our analysis. So I can also look at the distribution on a categorical basis of the product. I can look at the correlation or a heat map of the correlation. So correlation is nothing but, understanding the relationship between the fields. As in, if one field is influencing the other, I can take the decision based on that information whether that field should be part of our model or not. So this is pretty handy in understanding or taking that decision. Similarly, a lot of other analysis, outlier analysis is also involved here. Alright, so you can do a lot of understanding from these graphs. Moving on, let's do something which is very particular to forecasting. So in here, so in a data, in a temporal based data, we usually talk about lags, as in the sale of products today, as in right now today, can be influenced by my sale in product, let's say 7 days ago. So this is saying that I have a 7-day lag or relationship in the data. So this understanding will tell us how to specify the parameters in our forecasting model. So this is one of the crucial and very important step in forecasting. This is also a visualization. As you can see, blue is the units sold in the data, which is nothing but our ground truth. In here you see 7-day MA. MA is nothing but moving average, and 30-day MA is 30-day moving average. So if we do a moving average analysis, which is nothing but taking lags of 7 days, 30 days, and taking the average of it incrementally, so to say, and aggregate them over time, you can see these graphs. So we see that 7-day MA is doing much better than the 30-day MA, which could indicate or to some of us that 7-day MA is more influential, but this is not concrete at this point. What we'll do right now, next, which is very interesting and I probably one of my favorite steps, is to decompose the components in the data. So every temporal element will have trend, will have seasonality, and whatever is left behind, which is what we call residual. This is the last one. So we can break the data down into these components. So how does it help us? Looking at the trend, if you see, this is the second one. The trend is very irregular. Usually we'll expect some kind of downturn, upturn, more smoother trend. But since it is irregular, we know that a more complex model will be required to capture these information. Similarly, in the seasonal component, which is the third part, it is very, very uniform, almost too uniform. So it will be very easy to understand this pattern from the model perspective. We don't need to do much of a tuning for this. And coming to the residual part. So luckily in here, we do not see any pattern in the residual, which means that after breaking the components down, there's nothing left behind. All the information is captured in the trend and seasonality, which is good news for us. For let's say, the residual did have some kind of patterns in it, then what we will do is we'll try to find out whether that information is available in fields that is not included in our base data, or we'll try to find whether more complex trend and seasonal components could help us. Excuse me. Alright, so based on this analysis, I have understood that we can go for a model like Serima or Serimax. I have gone with Serimax because this is the example I want to show you. So Serimax will allow me to define all the trend, seasonality components, differential components in the model. So let me show you what it looks like. These are the parameters for the model. Hang on. I just skipped down. Yeah. So this is the model parameters. So based on that analysis, I can define at least a base combination of the PDQ or PDQS components here. So here I have taken 7 days lag, seasonality to be 7, and so on. But this is something like a base model I'm creating. So after understanding the performance with this simpler model, I can go for tuning the hyperparameters of this particular model. So it is not something I need to curate manually, which is good. So this, based on the analysis, I will have the parameters. I'll train my model now on the training data that I have, and I will test it on the holdout testing data. So because it is temporal component, the training data will be in the initial phases, let's say from here 22 to 23. Rest of it will become our training data set. As you can see here, red is the forecast and black is the testing data. So we are comparing how our forecast actually compares with the testing data. So as you can see here, it's not too bad. It is almost following the test data pattern. That means we are able to forecast properly as expected from the ground truth. But as it goes ahead, it is kind of losing its predictive capabilities. So this is one indication that model needs some improvement. And also we can look at the error component here. So this is RMSE and ME error component. It basically tells us how off our forecasting has been based on the data that we have, the test data. So if we cannot tolerate such a big number, we can optimize the model further, reduce this error, and once we're happy with it, we will deploy it to production and retrain it from time to time and use it to forecast our future sales of product, basically. So this is what forecasting looks like on a very, I wouldn't say it was basic, but it was, we could go further down the rabbit hole, but this is basically what we do in forecasting analysis. So alright, this is all I have. So any questions?
Thanks so much for great insights for this forecasting. So I believe that, let's say, in your like day-to-day work, like let's say for this training data, like how much like usually like you are working with the data, like what's the kind of volume of that? Is it like huge number of the data or?
That's a good question. That's a good question. So, in building a model, the amount of data is very crucial. So, because we are trying to understand the pattern in our past data, the more data you have, better for us. And even especially for time series analysis, because we are trying to predict the future events, it is usually very crucial to train the data as close to that future event as possible. As in, you'll be retraining this particular model more often than you would do any other type of model training in production. All right. What else?
Thanks so much.
I also have one question. So on the last part, like you showed this Ceramax model. So how do you incorporate these external trends that are not seasonal, like the market changes, or like today's very famous thing, like a product suddenly becomes viral and things, and
Yeah,
how
yeah.
are these, let's call them like anomalies or something, are those like kept in on the forecasting data for the future, or models are already adapted to it, or they're like
That
filtered
that
out? How
is
does it work?
fantastic question and very practical as well. So we can. It's all about the data. So let's say you're talking about the viral trend in data, right? We need to capture that data. So it can come from Twitter, let's say. That means we'll have to collect that data and we'll scrape Twitter and all those things. We'll clean it up, be ready for the model. That is option number one. When it comes to other fields like holidays or some inherent knowledge that we expect the model to have, we can also use profit from Meta. So that Meta is inherently very capable of capturing this kind of external patterns and trends. So we can use profit model, very robust for forecasting, and then on top of that we can supply this Twitter data or our own business data and make it more robust. So that is a great way to do it. All
Great.
right.
Thank you very much.
So no more questions, Atakan?
Oh, thank
Uh,
God. Okay.
if you have time, I was just gonna ask like one more thing, but like, it's like as like a closing question, as a like in the just layman terms. So the saying like the correlation does not imply the causation. So like when you build this forecast models, what steps do you take to make sure that like these trends are not just correlations, but they're actually like accurate projections? Like in layman terms, like, or is it like because at the end you showed that the model was getting a bit not accurate on the last graph. So how does it achieve? How is it achieved? Like not in a technical, but like in a straightforward, like easy way.
So, okay. So, correlation, if you remember the heat map that I showed of correlation. So, there what we are looking at is whether one field influences the other. So, like you said, I influence the other field. I'm one field, influence the other field, but that doesn't mean I cause its movement towards that. So now we actually expect correlated fields to be used in a way that let's say the units sold is correlated to the weather for some reason. Obviously it cannot cause the weather and the weather cannot cause the units sold. So what we'll do is we'll use one single field out of those two pairs because we do not want the model to be overwhelmed or have a bias because these two fields are going towards the same direction. We don't want it to have that bias. So correlation is important in that way. Causation we will not worry about at this point, luckily. So that is how we use correlation to build the model, basically.
Right. Thank you very much.
All right, thank you.
Yeah, thanks so much. Truly appreciate for the topic like in the data engineering and this time series analysis. So guys, that was it from our guest speaker, and I hope it was helpful and beneficial for others who was also pursuing their career in data engineering. And apart from that, like as we mentioned already, like every week, like we have one or two dev stand-ups, which is the purpose of like sharing the developers and IT people experience with others across the world. If you have any topic, if you want to be our guest speaker, please fill in the form on the description below. and we'll contact you, and then like you can be our guest speaker as well. So thanks so much, and have a great evening. Bye bye.